The first topic in this class that is really business calculus is section 10.1, limits. So first let's define what a limit is, and then we'll talk about how to write it. The limit is what y value is the graph or equation approaching and by approaching, what I mean by that is just getting close to. We're going to have some graphs that might have some open circles, but which value is it getting close to as x does something or as x approaches some value. So we may be learning some notation that's new to you, but if you will remember this, it'll make this whole lesson a lot easier to understand. When you're being asked to find a limit, you are being asked in some form or fashion what the y value is, okay, either visually or looking at an equation or something like that. So notation is simply how we write things in math. So this is the limit as x approaches a of f of x. That's literally how we would say that, so let's write that in quotation marks. The limit as x approaches a of f of x. And whatever we get for the answer will just be a y value, and we're going to call that in this case L. So the limit in this case is called L. So as x does something, as x gets closer to some value a, then I'm being asked to find what y is getting close to. And in this case, y gets closer to some limit quantity that we're calling L here. All right, so the first type of limit we're going to talk about is called a one-sided limit. And just like it sounds, it's going to be a limit from one side of the graph or the other, either from the left or from the right. So let's talk about the notations for both of those. A limit from the right, we're going to look visually at an example of this, so if you're not really sure what I mean, it's going to be explained in just a bit. So if I have the limit as x approaches a and I want to indicate that the limit is coming from the right, I'll indicate that by either a plus or a minus sign after the value. And then I have my f of x function here, okay? Just so you know, these letters, the limit and the x approaches a, are usually pretty small. So if I want to indicate something comes from the right, I use a plus sign after my value. If I want to indicate the limit is from the left, not surprisingly, it's going to be the same type of notation, but we're just going to use a minus sign instead. So the limit as x approaches a from the left of f of x would look like that. So if this is new to you, as you practice this, practice saying that. Practice reading this. I know it's strange notation, but it's certainly notation that we're going to hold on to for a while. All right, so let's look at a couple problems where we're going to be asked to visually find different limits. So I'm going to project this picture. Sorry about that. This graph. Put some tape so it doesn't slide around. Okay, so notice this graph is in pieces. We call this graph in algebra a piecewise function. Can't talk today. It's called that because it's in pieces, right? It's two different patterns. So you should have briefly talked about piecewise functions in college algebra or business algebra. It's okay if you don't remember it. I'll review it a little bit more here, but it shouldn't really be the first time you're hearing the term piecewise. Piecewise functions are just two or more functions pieced together. And so we actually find that these come up in real-life application classes like this one, because essentially all it is a pattern change. And those happen in the business world all the time. In other words, maybe we have a revenue function. The revenue pattern was this for the first 10 years of business, but then something happened in the economy and the revenue function changed after that. So they're just pattern changes, and frankly, they happen all the time. We just maybe might not like the way the graphs look. So I'm going to ask you kind of a series of questions based on this picture. The first two are actually not new material. They're actually older material. So if I ask you to find f of negative 1.5, f of anything, f of x just means y. Okay, so I'm asking you to look at the graph, and I'm asking you, tell me what the y value is when x is negative 1.5. So I'm going to kind of point that out with my finger here. So here's x equals negative 1.5. The question is, what's the y value here? So notice if you go up, you'll find that the y value is 2. So f of 1.5 is 2 in this case. Okay, what about if I ask you for f of 2? Now f of 2 is again asking you for the y value. So what is the y value when x is 2? Now notice here we have an open circle above 2, but we also have a closed circle. Open circles mean they're not actually part of the graph, it is open. So we would want to look for this closed circle. So what is the y value when x is 2? The answer is 2, not 1, since the 1 is open. So the answer here is 2. So those two questions are kind of older algebra type questions. Now let's get into maybe some of these limit questions. So the first part of these limits questions is just frankly learning how to read these. So if I give you this notation, what am I asking you for? Let's read it first. The limit as x approaches 2 from the right. Remember, a plus sign or a minus sign after the number indicates which direction we're coming from of our function f of x. This just indicates that, hey, we want to be looking at this function called f of x. Okay? So here, if we find x equals 2 here, we want to look at what's happening as we approach x equals 2 from the right. So notice we have a left chunk of the fraction or of the function and also a right chunk of the function. We want to look on the right chunk of the function. So if you were like a little ant traveling along this line and you were approaching x equals 2 from the right, what are you going to end up at, or what are you getting close to in the y? You're getting close to 2. So what about this pretty closely related question? Now notice this looks very much the same, right? The only change is you would read this, what's the limit as x approaches 2 from the left? We're still talking about positive 2. That minus sign after the 2 just tells you which direction we're coming from. So here's x equals 2. That's where we're going to focus our gaze. So as we approach, if we're a little ant crawling on this graph and we're approaching x equals 2 from the left, we're getting really close to y equals 1. Notice in this case we just approach it. We don't actually reach 1 since 1 is an open circle, but we're trying to write down what y value are we getting close to. And we are definitely getting closer and closer and closer to 1 the closer we get to 2 from the left. Okay, what if I asked you what is the limit as x approaches 4 from the right? Okay, so here's x equals 4. Okay, if I am a little ant crawling on this graph, if I approach x equals 4 from the right, notice my y value is getting close to 4. Again, it's an open circle, but I am still approaching y equals 4 as I get close to 4 from the right. If I ask you the other question, limit as x approaches 4 from the left, I still focus my attention here, right? But I come and I travel to x equals 4 from the left direction. But notice in this case, I end up with a y value of also 4. Okay? In other words, if you decided to move towards this x equals 4 from either direction, notice there's a single point I'm meeting at as opposed to this value that has a jump, right? We approach different values if we come from different directions. All right, so you can always pause the video if you want to look at the graphic just a little bit more or look at the graph. But this is really more of an exercise, a visual exercise than it is anything else. So like I said earlier, I put stars by things that are important, things that you will need to remember. So we've been talking about one-sided limits. Now let's talk about two-sided limits. Okay? When no plus or minus sign is listed after the value that x is approaching, then it's understood to be a two-sided limit. And just to be honest, these don't always exist. But if they're going to exist, this quality has to be met. The right side limit must equal the left side limit. Okay, so let's write that out kind of in everyday words. The left and right-sided limits must be the same for the two-sided limit to exist. Okay, so the key here is if you have agreement on the left and the right-hand side, then we would say the two-sided limit does exist. So just some other notations. Often we're going to find that actually the two-sided limit does not exist at all. And if we're going to say that, we have an abbreviation for that instance. If it doesn't exist, we use the abbreviation D&E. We would say the limit does not exist. Okay? D&E just stands for does not exist. Okay? So, for example 1 above, and my whole answer isn't really on screen, but you can look back up at your notes. Hopefully you're taking these notes kind of with me as we go. But for example 1 above, if I asked you to find the limit as x approaches 2 of f of x. Now notice this time I did not indicate a direction. So I'm going to kind of slide this paper up so that I can see the parts that I really want to up here so it's all on one screen. So when I don't indicate a direction, I'm asking you for a two-sided limit. So if we go back up and we look at parts C and D that I'm pointing out here, notice that if we come from the right, the answer's 2. If we come from the left, the answer's 1. In other words, they're not in agreement. They're not the same. So we would say that the two-sided limit does not exist as x approaches 2. Okay, but what if I asked you for the limit as x approaches 4 of this function f of x? And again, I'm looking up at example 1, so I'm going to slide this a little bit because we want to look at parts E and F for this one. So notice here, again, I'm being asked about the double-sided limit, the two-sided limit. If I approach 4 from the right, I get 4, and from the left, I get 4, which means the two-sided limit does exist and it's equal to 4. Okay, so I'm going to circle this whole thing. This is the phrase you would say. You would say the limit as x approaches 2 of f of x does not exist at all. The limit as x approaches 4 of f of x does exist, and the answer to it is 4. Okay, so let's do another kind of visual example. So let's look at this kind of strange looking piecewise function. Notice this is really kind of all in pieces, right? We have a curve over here, we have kind of a hanging point here, kind of all over the place. So I'm going to ask you some different values. And let's practice maybe you being able to read what it is that I'm asking you for here. So I'm asking you for the limit as x approaches 2, and then the plus sign after it indicates I'm asking you to come from the right. So you focus your attention at x equals 2, and you come from the right. So again, if you are traveling on this curve from the right and you're getting ever closer to x equals 2, what is the y value getting pretty close to? The y value is getting close to what looks like -3, right? So the limit as x approaches 2 from the left, notice that's a completely different question. I'm still looking here at x equals 2, but I'm traveling on the equation from on the left side of 2. So if I travel on the left side of 2 and get close to 2, notice I approach +3. So if I ask you the question, what's the two-sided limit? And remember, it's understood to be two-sided if I don't indicate which direction I'm coming from. You would go back up and look at these one-sided limits and notice, hey, I don't have agreement here and here. Okay, so the limit is different if I approach 2 from the right versus the left. So what would we say if the limit does not exist? We use the terminology, the limit does not exist. And when you do your homework on MyMathLab, that will be a multiple choice option for you. If it's asking you for the limit and the limit doesn't exist, that will be a choice that you can click on and choose. All right, so last one for this one, and then we're going to look at maybe some generalizations and some different types of problems. All right, what about the limit as x approaches 0 of f of x? Now notice what I didn't tell you. I didn't indicate from the left or from the right. So if I don't tell you that, it's understood to be a two-sided limit. And so what I like to do here is you can either do each side and kind of individually figure out the one-sided limits, or you can just visually say, okay, I'm just going to get ever closer to 0 and I'm going to squeeze in on it from both directions and see if I have a common y value that I'm getting close to. And notice I do, right? If I come from the left, I get close to this y value. If I come from the right, I get close to this y value. So the limit does exist, and the answer is 2. Okay, so these two are one-sided limits, these two are two-sided limits. Okay. So the gist, most of the time you're really going to be asked about two-sided limits. But if the graph appears to approach different y's, depending on which direction you come from, then the limit does not exist. If there's any confusion about which y value you should talk about, then it's probably that the limit doesn't exist. Okay, so if you have different y's, then the limit doesn't exist. Okay, simple enough, hopefully. Okay, so the first exercise is us looking at graphs, which we just did in the past two examples, and trying to figure out what the limit is. Remember, limits are always what is the y doing as x does something. But a lot of times we're maybe not going to have a graph. Perhaps we have a function instead, just an expression or an equation or something like that. So when trying to find limits of functions in equation form, so maybe such as polynomials or rational functions, we're just going to try an old algebra trick on most of these types of functions first. We're going to try to just plug in the x value, since what we're searching for is the y value for being asked to find the limit anyway. Then we're just going to plug in the x value, and oftentimes that will find our y value. And remember, we're doing that because the y value refers to the limit. Okay, I'm going to underline this word try here. Okay, we're going to try to plug it in. We're going to find out that sometimes that works well and sometimes that doesn't. We're going to talk about what to do when it doesn't work well. All right, so let's do a few examples. So let's practice how to read these. The limit as x approaches 1 of 2x cubed minus 4x squared plus 3. Okay, so that's a polynomial function, and I'm being asked to find the y value because I'm being asked to find the limit when x gets close to 1. Well, for this one, we can just plug in 1, and by that I mean everywhere there's an x, we're going to replace that x with 1. And we can use a calculator, although I don't really think we need it for this one since 1 is fairly easy to plug in. 2 minus 4 is negative 2, and then plus 3 would be 1. Notice this is the y value when x is 1. Okay? When x gets close to the value of 1, y also gets close to the value of 1. All right, so sometimes you might see a one-sided limit. I wanted us to do one where maybe we had a negative number, but then also the negative sign after, just to make sure we know how to read that. So So you read this, the limit as x approaches negative 5 from the left. Okay, the negative sign after indicates direction. And you don't do this one any differently. Like, it doesn't matter that it's a one-sided limit. We're just going to try the plug-in method and see if that comes up with an answer we can be happy with. So if I plug in negative 5, okay, then I'll get absolute value of negative 5 plus 3 divided by 5. So if I add negative 5 plus 3, I get the absolute value of negative 2. May have been a little while for you, but remember, absolute value answers are always positive. So I end up getting positive 2/5. So when x is negative 5, or when it's getting close to negative 5 from the left, y is going to be getting ever close to the value of 2/5. All right, one more, and then we're going to talk about what to do when maybe this plug-in method doesn't work. It'd be nice if it worked all the time, but frankly, it just doesn't. So the limit as x approaches negative 3 of the square root of 2x to the 4th plus x squared. So the plug-in method, I'm going to plug in negative 3 to the 4th, 2 times negative 3 to the 4th rather, and then plus negative 3 squared. Okay, you can use a calculator for this, but make sure when you have a negative number you're raising to a power, you'll want to put that in parentheses in your calculator. But let's say we get the square root of 171. Okay, this answer is correct, but it is not simplified. And MyMathLab, if you were to punch in an answer like this, it will try to give you an idea of that. It'll say your answer is correct, but it's not fully simplified. So you need to remember how to split up or how to do roots. We can't do the square root of 171 and get a whole number answer. So what you do when that won't happen is you try to find factors of 171 that are perfect squares. And it turns out that 9 times 19, which you could do a little work on your calculator and figure it out. 9 times 19 is 171. And then we can take the square root of 9, which is 3. So the simplified answer is 3 square root of 19. This is what MyMathLab would want. Okay, so it'll try to, if you try to enter in an answer like square root of 171, it'll say, hey, your answer's correct, you just need to work on simplifying it. Okay, so as x gets close to negative 3, y gets close to this quantity, 3 square root of 19. All right, so I had you underline that word try for a reason. So let's talk about what happens in a problem like this. So what about the limit as x approaches 2 of x squared minus 4 over x minus 2? Maybe you don't see a problem with that, so let's try our plug-in method. Let's try to plug in 2. Notice that when we do, we get 0 over 0. Now, a long time ago, you have probably talked in other math classes about how 0 is not allowed to be in the denominator. This is an undefined quantity. In other words, 0 over 0 doesn't tell us anything about what the answer is. We have two kind of things at play. Most of the time, 0 on top of something would mean the answer is 0. In other words, 0 divided by a number is 0. But then we have this 0 on the bottom, and it just throws the whole thing off. Okay? So in this case, you wouldn't have an answer from the plug-in method. Okay? So I like to call the method we've been using the plug-in method for obvious reasons. We're just plugging the number in. But if the plug-in method gives you 0 on the bottom, then you're not finished and you need to try something else. It means your answer can't be found by using that method. So I'm going to give you a couple of pointers on what to do if you get 0 in the denominator, because if you do not have your answer right now. Okay, so when you get 0 in the denominator, we don't say, oh, this is a problem I can't do. We just need to find something else to do. And so one of the things that you want to try, so before you try to plug in an x value in a limit problem, sometimes it's going to be helpful to factor it. So we practiced factoring in that review lecture, remember? So if a problem can be simplified by factoring, then you'll want to go ahead and do that. Okay. It should be noted, though, that any point, you're not really canceling terms out, so I want to be kind of clear there. But any point that is, so I'm going to put quotes around this, canceled out. It's not really what you're doing, but essentially it kind of looks like that. It basically indicates a hole in the graph at that location. And we'll talk about that with an example here in a bit. Remember in examples 1 and 2 where we were looking at the graphs where we had holes in the middle of a line? That's what would indicate a hole right here if you're canceling out terms, or kind of air quotes canceling out terms. So let's look back at that example that I just asked you, what do we do about this one? So let's look at the limit as x approaches 2 of x squared minus 4 over x minus 2. We already tried it above and we noticed, hey, the plug-in method gives us something strange, right? We can't have 0 over 0, so something's wrong and we need to try to fix that. So we're going to try to see if we can algebraically simplify this at all. Now this is one of those special case factoring problems that we talked about in the review lecture. So this is a difference of 2 squares, so it factors into x plus 2, x minus 2. Notice the bottom stays the same. But notice we have some repeat factors on the top and the bottom, right? So I'm going to use a different color. Remember, we're not truly canceling it out, just for the purposes of limits, we're canceling it out. So before we talk about the answer, I want to make sure we're clear here. There actually is a hole in the graph at x equals 2. It's x equals 2 because you would actually set this equal to 0, and when you did, you would add 2 to both sides. Okay? But for our limit purposes, notice now we're trying to find the limit as x approaches 2 of x plus 2. Notice now if I try the plug-in method, I no longer have a problem with getting 0 in the denominator because, frankly, I don't have a denominator at all. So if I plug in 2, I get 2 plus 2, or 4. So essentially, I simplified out the problem area of this question. The problem area was the denominator, and I kind of got rid of that. That's kind of the point of this method. Okay, so let's look at another one. So let's say that I want to define the limit. And we're going to do 2 parts for this. Let's say I want to define the limit as x approaches 3 of x squared minus 5x minus 36 over x minus 9. Now, you'll need to refer back to the review lecture that we talked about last time. If you're uncomfortable with factoring, you're going to need to get comfortable with factoring. But actually, maybe we don't even have to factor this quite yet, because let's try the plug-in method. That's always what you should try first. So try to plug in 3 everywhere there's an x. So 3 squared minus 5 times 3 minus 36 over 3 minus 9. So I'm going to get 9 minus 15 minus 36 on top. And I'm going to get 3 minus 9 on the bottom. So if you simplify that, and you can use your calculator to do that, you will get negative 42 over negative 6, which just simplifies to 7. Again, MyMathLab, if you try to enter in the answer like this, it's going to tell you, hey, your answer's right, but you need to simplify it. Okay? But what if I ask you about the limit as x approaches 9 of x squared minus 5x minus 36 over x minus 9? Now maybe you can see ahead of time what's going to be a problem here. Okay, so if we try the plug-in method, and again, that's always what we want to try first, we would have 9 squared minus 5 times 9 minus 36 over 9 minus 9. Okay, so you can maybe see the problem we're going to have in the denominator. We're going to get here 0 over 0. Sometimes you'll get a number over 0, but this time we got 0 over 0. So again, this is undefined. Okay, so we don't leave the answer that way. Okay, we try something else. Okay, so we're going to try something else. And that something else is there any sort of simplification that can be done that might allow us to do this problem? In other words, can I factor or simplify or something? So notice I'm leaving this limit notation, limit as x approaches 9. So you need to go back and maybe review, but let's practice factoring. Okay, so go back to the first lecture that we had if you're shaky on that. But this factors into x minus 9, x plus 4. Okay. So remember, we use AC method if you need help on that. Notice what that does, right? That cancels these x minus 9s out. And then I have eliminated the problem. So now I'm finding the limit as x approaches 9 of x plus 4. And notice now the plug-in method is just fine. I can plug in 9 and I get an answer of 13. Okay, so we try the plug-in method. If the plug-in method doesn't work, we try to simplify. Sometimes even maybe that doesn't help us all that much. So I'm going to briefly show you this. This is probably not very many people's go-to method. But I want to show you one, maybe a simplified example. So let's say, I want to remind you what an algebraic table even looks like too, so it's a good review problem. The limit as x approaches 2 of the function x squared plus 1. But let's say that I indicate that you have to complete a table to solve this one. Now, our plug-in method would work just nicely for this problem. I'm just choosing kind of a simpler problem to show you what the table method looks like. In other words, we could actually just plug in 2 here. We'll get 2 squared plus 1, which is 5. Okay, but this is what a table looks like. It looks like the XY tables that you're used to from algebra, but instead of y, we're going to say f of x. And remember, these tables were used a long time ago in algebra for you when you needed to graph something, and maybe you weren't sure what the graph looked like and you were able to choose any x's you wanted, and then you plugged them into this equation to get your y's. But this time we need to make sure we're picking x's that are close to 2, because that's what this problem indicates. X is getting close to 2. So you may not like the x's I'm about to pick, but I'm going to pick 1.9. And why am I picking 1.9? Because it's pretty close to 2. Okay. But then I'm going to get kind of closer to 2. If this is close to 2, this is even closer, right? And then we'll go one more, and then maybe you'll see the idea. So this is close to 2, even closer. This is even closer than that, right? All of these values are close to 2, okay? But notice all of these are smaller than 2. So we're also going to do the same thing for values that are bigger than 2. In other words, values to the right of 2. So 2.1 is pretty close to 2. But 2.01 is even closer, and 2.001 is even closer. Okay, so I could have picked any values I wanted here. The reason I chose these is because these are all close to x equals 2. And when I'm trying to do the limit as x approaches 2, that's what I want. Okay, so you would use a calculator and you would plug in 1.99 in for x. So literally you just do 1.9 squared plus 1. And if you do, you get 4.61. And then do the same for everything else. Plug in 1.99. So 1.99 squared plus 1 would be 4.9601. 1.999 squared. So I'm getting all of these from my calculator. I'm not doing these in my head. Okay. Now let's go to these, right? 2.1 squared plus 1 would give me 5.41. Here I get 5.0401. And here I get 5.004001. So you can pause this video and just verify with a calculator that yes, if I plug these x values in, I get these y values. But what you need to be paying attention to, remember what I said at the very beginning of the class, what I'm looking for with a limit is what are the y values doing as x does something. Okay, and notice that these y values do have a pattern. Okay, they're getting close to something. And so I want you to try to think about what you think they're getting close to. They're getting close to 5. Okay, notice even more than that. This was close, closer, and still closer to 2, right? And notice these y values get closer and closer to 5, okay? Same thing here, right? This is close to 2, even closer, the closest, and these values are close to 5, even closer, the closest to 5, okay? So in other words, you're looking for a trend in the table. So as x gets closer to 2, then y gets closer to 5. Okay, remember that's what we were looking for. So how you would write this is the limit as x approaches 2 of x squared plus 1 equals 5. Okay. By the way, we're not going to do another one like this, but if you had a table where the y values don't seem to approach anything, then we would say that the limit doesn't exist in that case. In other words, if you have a table where the y values are just getting super large and they're just getting bigger and bigger and bigger and they're not getting close to something like they are in this table, then you would say the limit doesn't exist. And that's a complete possibility when you're doing problems like this. So I've taught you 3 ways to find limits. So I want you to write these down in order. Here are your strategies for finding limits. Okay, your first method should always be to plug in x. That is going to work a good portion of the time. Okay, so try plugging in x and see what happens. Okay, if that fails, remember what I mean by fail, right? That would mean you got 0 in the denominator. Try to factor and simplify, like we did in some of the previous examples. And then once you've simplified, see if that helps. Then plug in x. Okay? And then last but not least, if both of those things fail and you're still getting 0 in the denominator and you're just not clear what to do, then you can try the table method. Okay? Okay, so we're going to try one more kind of strange piecewise function, and then we're going to look at one little bit of a different topic before the end of the lecture today. So we talked about piecewise functions at the beginning of class. This is what a piecewise function looks like in equation form. It's f of x equals and then a curly brace, and so basically it's a change of pattern. We're going to follow this first pattern as long as x is less than 0. But then when x goes greater than 0, we're going to switch to the second pattern. Okay, that's really all that means. So all it requires is that you really know how to read this piecewise function. So let's say that I asked you to find the limit as x approaches 2 of f of x. Okay, so the question is, I want to try the plug-in method, but the question is, which equation do I use? Which one do I plug it into? And it's always going to have to do with what your x value is. Okay, so you're going to say x is 2, and your question to yourself is, does that fit into being less than 0, or is that greater than 0? Notice 2 is greater than 0, so since 2 is greater than 0, when I look back up at the problem, I need to use equation 2. Once you decide which equation to use, we're just going to plug it in. So it's going to be 2 over 2 minus 3. So we get 2 over negative 1 or negative 2. Okay. What about this? The limit as x approaches negative 4 of f of x. Okay, so we're going to try the plug-in method, but again, the question really is what my x value is, right? I'm getting close to x equals negative 4, so is that less than 0 or is that greater than 0? Okay, notice negative 4 is less than 0, right? So we're going to use equation 1. That's just a mistake there. So if we plug in negative 4 over negative 4 plus 3. So we'll get negative 4 on top, negative 1 on bottom, and so the reduced answer is just 4. But what about if I asked you for the limit as x approaches 0 of f of x? Now notice what the problem is, okay? Notice that if x is equal to 0, I don't really know which of these equations to look at. In fact, this piecewise function doesn't include 0 on either side, which actually means there's an open circle at 0, okay? So what we have to do in this case is we just have to look from both directions, and remember what we decided. It will have a two-sided limit as long as the different directions kind of agree with each other, okay? So let's just kind of in our mind do that. If we were to plug in 0 on the left of x equals 0, right, we would get 0 over 3, which is 0, right? If we look at it from the right of x equals 0, we'll get 0 over negative 3, which is also 0. Notice we have agreement here. So the answer here is 0, okay? And the reason is this is the y value no matter which direction we come from. So in this part C, we weren't really sure which equation to use, so we just looked at both and made sure that they agreed. We didn't have to do that for A and B since we were already knowing which equation to use, either the first one or the second one. All right, so the last thing that we're going to talk about is something that you may have briefly discussed in algebra, but I'm going to accentuate briefly, so briefly that you may not even remember it. So we're going to kind of take it from scratch. So you may have talked about something called the difference quotient in algebra. The difference quotient looks like this. Okay, so I'm going to read that. F of a plus h minus f of a all over h. But we're going to put a little twist on that. So we're going to talk about the limit of a difference quotient. And this is actually going to have some pretty big significance in this class over the next couple weeks. In other words, there's actually a reason I'm teaching you this. So let's talk about the limit as h approaches 0 of that difference quotient. Notice all I did different was I added in a limit notation. So you would read that the limit as h approaches 0 of f of a plus h minus f of a all over h. Okay, so these problems look a little more tedious than they really are. I promise if you can take this a step at a time, I think you'll find it's not as ugly as you might think. So if I give you that f of x equals 3x plus 8, I want you to find the limit as h approaches 0 of f of a plus h minus f of a all over h. Notice I'm just repeating that limit of a difference quotient. I had you write it again because, again, this is going to be actually an important quantity over the next couple weeks. So because it's been a while since we all learned algebra probably, I'm going to do the parts of this equation separately. This is maybe a little intimidating of an expression to look at, so I just want to talk about what f of a plus h would be separately for a minute. So remember from algebra, f of something just means plug in whatever is in the parentheses in for x. So instead of 3x plus 8, we're going to have 3 parentheses plus 8. Notice the structure here and here is the same. We're just replacing x with a plus h. So we'll do a little bit of algebra to kind of simplify this. We're going to distribute that 3. So we're going to end up getting 3a plus 3h plus 8. I'm going to circle this. Notice I can't even go any further here because I don't have any like terms, right? I have an a term, an h term, and then a constant. Okay. So let's look over here. I figured out what f of a plus h is. Now let's talk about what f of a is. That's actually a lot more straightforward. Remember, f of anything means come up to your f of x equation and replace your x with whatever in the parentheses. So instead of 3x plus 8, we're going to get 3a plus 8. So I'm going to circle that. So I'm going to kind of box this in over here. This is what I would call side work. This isn't really necessary if you're super confident in your algebra skills, but it's just a way to kind of work the sub parts off to the side. So let's come back up here and maybe put it all together. So I'm just copying down this here. So I have the limit as h approaches 0, and I'm going to have something over h. Okay, but let's put in what we figured out off to the side in here. What was our f of a plus h over on the left? Well, we got 3a plus 3h plus 8 for the f of a plus h portion, right? So I have f of a plus h here, and now I want to subtract f of a, but that's over here, right? I got 3a plus 8. Notice I'm putting parentheses around each of those parts so I keep them separate. Okay, so now let's see if there's any simplification. So this minus sign can actually distribute to both of those things. So let's write down the next step. Notice every step along the way I'm continuing this limit as h approaches 0 notation. So the first parenthesis stays the same. But the second parenthesis, notice the minus sign is going to change the sign in both terms. So minus 3a minus 8 is what I have. And now with just a little arithmetic / algebra, we can kind of simplify, right? Combine like terms. 3a minus 3a is 0. 8 minus 8 is 0. So that big ugly list is a little shorter now. I have limit as h approaches 0 of 3h over h. Okay, now because I'm multiplying 3 times h, I'm actually allowed to cancel one more thing out. Okay, so I can cancel the h's here, and then I am left with the limit as h approaches 0 of 3. And so notice normally I would try the plug-in method at this point, but there is no h to plug 0 in for, so in the end we just get an answer of 3. Okay, I started you off with an easier one. It's kind of honestly an uninteresting one when you're talking about the limit of a difference quotient, but we just get an answer of 3. Okay, by the way, notice we were not allowed to just do the plug-in method up here. Notice if you plug in 0 here, or even here, notice what you're going to get in the denominator. You're going to get 0. Okay, but by the end, we no longer had a denominator and we could treat our limit accordingly. All right, so last problem of the day. I hear cheers from your houses / apartments right now. This one is more like what I would expect to ask you about on a test, just so you know. Example 10 was more of a kind of get your feet wet example. This example is much more like what I'll ask you about. So notice I called the function g this time. So the limit of a difference quotient looks the same except in place of in place of f, I put g. So again, my strong suggestion is that you try to figure out the parts off to the side. And by the parts, I mean, let's figure out what g of a plus h is and work that out. Then let's figure out what g of a is, and then I can come together and put those in the problem. So let's talk about g of a plus h. Okay, remember, g of anything means replace x with that. So instead of x squared minus 2, I'm going to have parentheses squared minus 2. Okay, it's really tempting. I know some of you want to do it. This is not a squared plus h squared. You are not allowed to distribute a power when you're adding. So let's maybe write it out differently, and then maybe you'll think of it another way. Something squared is just something times itself. Okay, well, when you see it like this, hopefully you realize that, hey, I am going to have to do FOIL here. Remember, we reviewed that the first class day as well in our review lecture. So FOIL stands for first, outside, inside, last. So first, a times a is a squared. Outside, a times h is ah. Inside, h times a is another ah. And then last, h times h is h squared. Don't forget to bring your minus 2 down. In problems like this, students forget that a lot. Okay, so we'll combine like terms. We have a couple of like terms. So we have an ah and another ah. So if you add those up, you have 2 of them. But notice nothing else is a like term. So this is as far as I can go with this part. Okay, I'm going to have to be okay that that's a little tedious. And let's talk about g of a. G of A should always be pretty straightforward. You're just going to look up, or F of A, or whatever letter we happen to be using, you're just going to replace x with A. So that's just going to be a squared minus 2. Okay, so I'm going to box this in again. This was just our side work. This is just what we're going to use over on the right. So now let's talk about what I have and put it all together. The limit as h approaches 0, and I'm going to have a bunch of stuff over h. I know that for sure. Okay, so let's start a piece at a time. What did I get for the g of a plus h part? Well, I got a squared plus 2ah plus h squared minus 2. Okay, that is my g of a plus h part. And now I need to subtract off what I got for g of a, which was a squared minus 2. And so just like in the last problem, the minus sign is going to distribute to both things, which means the signs are going to change. But in the first part, notice we just rewrite that. So it's going to be a squared plus 2ah plus h squared minus 2, and then minus a squared plus 2. Notice I changed the sign here and here. Okay, just a little side note before we do some cancellations. Remember, if you plugged in 0 at this stage, you would get something that was undefined. You're not allowed to do that yet. Okay, our goal is essentially to get rid of this h on the bottom, but to do it correctly. So a squared minus a squared, that's gone. That's 0. Negative 2 plus 2 is also 0. So notice I got rid of some pairs, right? But I still have a couple of things left. So I've got 2ah plus h squared over h left. And don't forget your limit notation. Notice still again, I cannot plug in 0 yet because I'll get 0 in the denominator and I'll have an undefined answer. So let's see if I can factor the top. You're only supposed to cancel h's out when you are multiplying. So if I notice that the top terms each have an h in them, if I factor out an h, I'll get 2a plus h. Okay, refer back to the first class day if you're curious about factoring, but they had an h in common. If I divide 2ah by h, I have this left. If I divide h squared by h, I have this left. Okay. And then I'm allowed to go ahead and cancel the h's now that I am multiplying on the top. And so in the end, I get the limit as h approaches 0 of 2a plus h. Notice what I've done at this stage. I no longer have an h in the denominator. So now, when I do the plug-in step, which I wasn't allowed to do in any previous step because of that h in the bottom, now when I do the plug-in step, I'm going to get 2a plus 0, or just plain old 2a. Okay. Notice a couple of things. I couldn't do the plug-in step till the very end until h was out of the denominator, and also I continued the limit notation step until I did the plug-in step. So until the very end, you're going to keep writing that limit as h approaches 0 step over and over and over. And that applies to all limit problems, not just these. Okay. So I urge you to go ahead and log on to MyMathLab and go ahead and try to start doing some of the problems from 10.1. And then the next couple of weeks, we're going to be using this limit of a difference quotient equation pretty extensively.